The LCT 613 cut-to-length line begins by loading the metal coil onto the uncoiler. The coil is then guided through the straightening machine to remove any curvature. After straightening, the sheet passes through precision rollers to ensure flatness and dimensional accuracy. Next, it enters the cutting unit, where it is cut into sheets of preset lengths. These cut sheets are transferred onto a conveyor and aligned automatically. Finally, the sheets are stacked neatly into bundles by the automatic stacking system. Throughout the process, the equipment operates smoothly with synchronized control, ensuring high productivity, precision, and safety for the operators. Molten slag is dumped from the slag furnace, and a large wheel loader approaches the slag pit, equipped with a slag bucket, which is designed to withstand extreme temperatures. The machine carefully lowers the reinforced bucket into the molten slag and scoops up the material. Thanks to the bucket's heat-resistant design, the excavator can safely transport the glowing, semi-liquid slag. After lifting the load, the operator steadily moves the machine out of the pit. Finally, the slag is dumped into a designated area for further processing or disposal, completing the efficient and safe processing cycle. The controllable pitch propellers for the 86-meter patrol boats were produced with fully integrated systems, including the control unit, transmission, and hybrid drive components. These 5-blade propellers are hydrodynamically optimized and designed for long-term operation. Key parts are easily replaceable, meeting strict serviceability standards. The system is adaptable for future use with water hydraulics. All components were manufactured and installed in coordination with Fassmer Shipyard's production schedule. The Sulzer Service Center in France begins by inspecting pump components and conducting detailed diagnostics. Worn parts are disassembled, cleaned, and either repaired or replaced. Using advanced CNC machines, new components are precisely manufactured. Engineers perform reassembly with strict quality control. Pumps are then tested under extreme conditions on a specialized test bed. Throughout the process, expert teams apply tailored solutions, ensuring high performance and reliability. The facility's modern infrastructure and environmentally certified space support efficient production, maintenance, and servicing of rotating equipment. The process begins with the CAD design of the mold, followed by precise CNC machining of large steel blocks to create the main cavity and core components. After roughing, the parts undergo heat treatment to enhance durability. High-speed milling machines then perform fine finishing on complex geometries, ensuring tight tolerances. Electrodes are prepared for EDM, which is used to form intricate details. Critical surfaces are measured and verified using 3D coordinate measuring machines. The mold components are then assembled, including installation of hydraulic cylinders, ejector systems, and cooling channels. Final polishing and surface texturing are carried out for optimal mold performance. Once assembled, the mold is tested on in-house 1,000-ton presses to simulate real production conditions. Adjustments are made as needed to ensure flawless function before delivery. This process applies to both injection and compression molds for automotive, technical, and sanitary applications. Located in Germany, Tesla's Gigafactory is a Tesla car manufacturing facility where we get a glimpse of how a car is made. The first part of the production process begins with the introduction of raw metal and components, followed by large stamping and casting parts. Here, large pieces of aluminum are forged, using high pressure for the body and chassis. Next, robots meticulously weld and assemble the body panels, turning the individual panels into rigid frames. After welding, the bodies move into the paint shop, where robotic arms precisely dip, coat, and spray each car, ensuring perfect coverage. After painting, the cars are transferred to plastic molding stations. Here, exterior components such as trim and bumpers are seamlessly fitted into the glossy, colored shell. The next stage is interior assembly, where mechanics install the powertrain components, seats, electronics, dashboards, and wiring. The cars take shape as these critical systems come together. Finally, each car enters the inspection area where technicians perform final checks for fit, finish, and function. Once fully cleaned, polished, and approved, the car rolls off the line, ready for delivery. The construction of precast concrete wall panels begins with plotting the wall element on a clean, flat casting surface. Workers carefully mark the panel's perimeter, door and window openings, and specific zones where embedded components will be installed. Using tape measures, chalk lines, and laser levels, they ensure that each dimension matches the technical drawings exactly. This precise layout is critical to guarantee that the final product will fit seamlessly on site. Following the layout, the next step is molding and placing electric and water installations. Workers attach formwork borders to define the panel edges and insert embedded components such as plastic conduits, junction boxes, and plumbing sleeves directly onto the casting surface. These components are placed according to the plotted lines and fixed in position using adhesive, screws, or brackets. Care is taken to ensure that all pipes and boxes remain stable during the concrete pour. This step allows for quick electrical and plumbing installation during building assembly. Next, the team moves on to inserting reinforcement, often referred to as ironing. Prefabricated steel mesh and rebar cages are lifted and placed inside the mold. These steel elements are arranged horizontally and vertically to follow structural specifications. Workers use spacers and wire ties to ensure the correct cover between the steel and the concrete surface, which is essential for long-term durability and resistance to corrosion. Openings in the reinforcement are made to accommodate the previously installed electrical and water components. With the rebar in place, the concrete pouring process begins. Freshly mixed concrete is poured in by pump. Workers distribute the mixture evenly throughout the form, using shovels, vibrators, and hand tools. The concrete must completely enclose the rebar and embedded items, leaving no voids or air gaps. Pay close attention to corners, edges, and around pipes to avoid weak points in the slab. Immediately after the pour, vibration and rotation take place. Internal and surface vibrators are applied across the mold to remove trapped air bubbles and compact the mix tightly against the mold and reinforcement. Once the first layer of concrete has been consolidated, the entire panel is rotated using a lifting crane or mechanical turner. The form is flipped vertically or horizontally depending on the setup, and a second layer of reinforcement may be added. Another layer of concrete is poured and vibrated to complete the double wall formation, where two thin concrete layers are joined with a hollow core that can be filled with insulation later. Finally, the finished panel undergoes curing and storing. After the concrete has gained sufficient strength, the mold sides are removed. The completed precast wall panel is lifted by crane and carefully transported to the storage yard. There, it is placed upright on steel racks or wooden supports to continue curing under controlled conditions. Each panel is inspected for surface quality, dimensions, and embedded element alignment before being approved for shipment to the construction site. The production of railway sleepers begins with the pre-production stage, which involves cleaning and oiling the molds, installing inserts, pulling and tensioning steel wires. Then, concrete is cast and vibrated into the molds. The sleepers undergo steam curing for 12 hours, ensuring strength and durability. The next day, the cured sleepers are cut and demolded, then transported to the pre-assembly area. The factory uses the long line method, with 8 production lines capable of casting up to 3,200 sleepers per batch. A dedicated batching plant supplies up to 380 cubic meters of concrete daily, using sustainably sourced materials. After production, sleepers go through rigorous quality checks, including dimensional control, cube testing, and bend testing. Once passed, the Vosloo W30HH fastening system is installed, and the finished sleepers are prepared for track installation. Handcrafted GmbH, with over 135 years of tradition, is a German company renowned for producing technologically advanced machine tools. Located in Gießen, a city of scientists, inventors, and academics, the company has continually set new standards in precision, speed, and perfection. One of its most remarkable innovations is the HEOR 4000, a world-unique, high-speed milling machine recently delivered to Germany's largest car manufacturer. This machine features revolutionary technology and exceptional thermal stability, achieving an unprecedented combination of precision and speed. The company product range includes turning, milling, and boring machines, serving both medium-sized businesses and major international firms. The company's core strength lies in the Hynoform and Hynomill series, known for their versatile milling applications. Additionally, their Hynomat and Hynoturn lathes, including slant bed machines and multi-technology centers, like the Hynoflex, address a wide range of industrial needs, from simple to heavy-duty machining. A key feature of the company's success is its in-house production, allowing full control over manufacturing and the ability to integrate continuous innovations. This company also operates its own Hynomill machine, both for customer orders and internal use. To ensure future growth, the firm maintains an in-house training workshop with over 20 apprentices, providing hands-on education and long-term employment, cementing its role as a forward-thinking, quality-driven machine tool manufacturer. At Brook GmbH, a complete range of in-house machining processes is performed, including turning, drilling, milling, and gear cutting. The company handles large components, such as turning rings up to 6,500 millimeters in diameter using vertical turret lathes. Drilling is accelerated with dual spindles, while milling operations shape large parts up to 6,500 millimeters using 5-axis simultaneous machining. Combined turning and milling can be done in a single setup to ensure high precision. Throughout machining, dimensional accuracy is maintained within hundredths of a millimeter. Final inspection is carried out on a 3D coordinate measuring machine in climate-controlled conditions. The production of box trumpet begins with the shaping of the bell, a key component that influences the sound of the instrument. Craftsmen hand hammer a flat sheet of yellow brass into a rough bell shape. The piece is then torched to soften the metal and carefully shaped with a mandrel. The mandrel ensures a consistent curvature, which is important for the sound. The bell is torched and struck by hand multiple times, then trimmed, ground, and welded along the seam before being fed into a hydraulic press to achieve its final flared shape. Next, attention turns to the mouthpiece, the narrow tube where the mouthpiece connects. The mouthpiece is made by grinding, welding a brass tube, and inserting a steel tube to maintain the internal dimensions. This ensures smooth airflow. A custom machine uses pressure to shape the tube with extreme precision, avoiding any distortion that could affect the tone or intonation. Next, the valve section, the mechanical heart of the trumpet, is assembled. The machinist uses a wooden hammer to gently tap the valves and the tuning slides into place, followed by a blowtorch to heat the valves. A small lathe is used to precisely machine the valve holes. The ports and holes on each valve must be perfectly machined to ensure accurate airflow when pressed down. Once completed, the valves are individually tested to ensure airtightness and smooth movement. Next come the tuning slides. These U-shaped tubes allow the player to adjust the pitch. Each slide is hand-welded and carefully fitted to its corresponding tube. This stage also includes the installation of brackets and supports to reinforce the entire structure. Hoti. Next comes the mouthpiece, the part that starts the sound. Each mouthpiece is machined from a solid brass rod. The exterior is turned on a lathe, while the inner cup, throat, and backbore are precision drilled using specialized cutting tools. After shaping, the mouthpiece is polished, cleaned, and either silver or gold-plated to provide a smooth, durable surface suitable for the player's embouchure. At this point, all the components are assembled. The bell, lead pipe, tuning slides, and valve section are soldered together using jigs to ensure alignment. Technicians inspect the assembly for symmetry and accuracy. Once the structure is confirmed, the instrument undergoes thorough polishing to remove any marks and prepare it for finishing. Finally, the trumpet is lacquered or silver-plated to protect the brass and enhance visual appeal. A technician then performs a final assembly, inserting the valves and aligning all moving parts. Each trumpet is individually play-tested by skilled musicians to ensure it meets box high standards for tone, responsiveness, and intonation. The fabrication of the 40-foot diameter Regenerator head with 11 Cyclone pairs by Contract Fabricators Inc. demonstrates a highly complex and coordinated process. The project begins with the cutting and preparation of massive steel plates, which are rolled into precise curved sections using heavy-duty forming equipment. These sections are then aligned and welded together to form the cylindrical body and domed head of the Regenerator. The fabrication of Cyclone components is carried out simultaneously. Each Cyclone is assembled from multiple precisely cut parts, which are fitted and welded with tight tolerances. CFI uses automated welding systems and overhead cranes to handle the weight and size of these units safely and efficiently. Skilled welders conduct full penetration welds to ensure strength and leak-free performance under high pressure and temperature conditions. Next, the Cyclones are mounted into the Regenerator head in aligned pairs. Extensive internal bracing and structural supports are installed to secure the Cyclones during operation. Final assembly includes welding the Regenerator shell to the Cyclone structures and performing thorough non-destructive testing to verify weld integrity. Throughout the process, dimensional checks and quality inspections are performed to ensure the unit meets stringent specifications. After painting and protective coating, the completed Regenerator is prepared for transport by barge or heavy haul. This project exemplifies CFI's expertise in large-scale, high-precision fabrication for the petrochemical industry.